And welcome back to the stage, Matthew Garrett.
So my name is Matthew Garrett. I'm at CoreOS. For anyone who's not familiar with CoreOS, we produce a suite of software ranging from the operating system up with the intent of making it easier to build and deploy container-based systems, because fundamentally we believe that container-based solutions make it easier to build secure systems. And I'm going to be talking about certain aspects of that today. So I'm not actually going to be talking that much about, well, at all, about things directly related to Sysdig, but more about how the container ecosystem as a whole is something that's advantageous both for developers but also for admins. How many of you have had to deal with software security at some point during your professional career? OK, some of you. And how easy have you found it to convince management that security is important? Yeah, not many of you seem to have really had a good sell there. How many of you have had pushback from other developers or from operations people when you've attempted to implement any sort of security? Yeah, a few. And the unfortunate thing here is that convenience often beats security, which is kind of understandable. If the service you're running isn't working, then it doesn't really matter whether it's secure or not. You're not running a service. And if your entire business model involves you running a service, there's something of a conflict there. So in reality, convenience is, in many ways, the favored party. There's definitely some rigging going on in this scenario. So when we're thinking about security, when we're designing things that are intended to be more secure, we need to design them with the mindset of how can we ensure that users will choose security? How can we avoid them choosing convenience instead? And in this case, basically, making the secure solution the better solution is the only thing that we've really found industry-wide that seems to work in this respect. If we're not able to make the secure solution fundamentally better, there's no incentive for someone to choose the secure solution. Now, this crowd's reasonably young for the most part. How many of you have actually used Telnet for its intended purpose? That's more of you than I expected. Now, one of the problems with Telnet, if you were ever a sysadmin, was that Telnet was not easily scriptable. When you telnetted somewhere, you needed to log in. You couldn't pass a command to Telnet and tell it, run this command on this other system. If you were doing any sort of interactivity, you had to basically script your use of Telnet, which was an unpleasant experience. And then there was that whole having to type a password thing, which meant that you couldn't meaningfully automate Telnet. So people came up with an alternative. How many of you ever used RSH? I'm so sorry. So for those of you who didn't, RSH was this wonderful thing where you typed RSH and then a system name and then hit enter. And it would ask you for your password, and you could type in your password, and then it would give you a shell. But the nice thing about this was you could also type RSH system name command, and it would execute that command on the remote system and then return, which meant that you could write nice scripting solutions. But the problem there was, well, you still need to have the password entered. So you could pass the password on the command line, but then you have your passwords hard-coded in a bunch of scripts, and if you ever change your passwords, that's all terrible. So there was something called the rhosts file. You could create a file in your home directory called .rhosts, and then you could put a host name in there, and then that host name was able to RSH in without a password, which was brilliant in a number of different and terrifying and upsetting ways. This was absolutely a case of convenience winning over security. People used rhosts because it was the easiest way for them to script deploying stuff or updating stuff or making any sort of configuration changes. You'd write a script that RSH'd into a bunch of systems and then reconfigure them. And then in the mid to late 90s, along came SSH. And SSH did everything that RSH did. This also encrypted it. And it also supported key-based authentication. So you could have the private key on one system and then public keys on a bunch of other systems. And then someone was no longer able to gain access to all your systems merely by spoofing DNS. So SSH was equivalent in functionality to RSH in a number of ways, but more secure, which was wonderful. But it also brought other benefits, like the fact that X forwarding worked magically without you having to type a bunch of extra commands. And people moved to SSH not just because it was more secure, but because it was fundamentally better than both Telnet and RSH. By building a tool that made it easier for people to do their jobs, it was easier for admins to justify migrating to SSH, and we got all these security benefits as a side effect. The only other way we can really increase adoption of security practices is by increasing social pressure while reducing the friction associated with something. The problem with SSL certificates in the past was that, well, firstly, in a lot of cases, the admins didn't gain any security benefit from them at all. It was the users who benefited in some way. And if your security work isn't benefiting you, it's, again, much harder to justify. But also, renewing your security, your SSL certificates frequently was a gigantic pain. So the easy thing to do was to just run something without any SSL. And then Let's Encrypt came along and made it possible to just script all your certificate renewals, and you could set it up once and then forget about it, and it cost you nothing. And since Let's Encrypt became publicly available, a significant percentage of the internet has suddenly become available over HTTPS that was previously only accessible over unencrypted channels. So those are some examples of where by either making it so much easier than it was in the past, accompanied by social pressure, or by building something that was both secure and also better, security became an easy sell within the industry. But many other examples have been failures. SELinux is a security module in Linux that allows you to build complex, basically arbitrarily complex policies that allow very fine-grained control over what individual applications on your system can do, which files they can have access to, how they can communicate with other applications. And adoption is not particularly widespread. Seccomp, which allows you to reduce the set of system calls that an application can make in order to increase security, is by and large in the general purpose computing world unused. A small number of applications set up their own Seccomp sandboxing, but the vast majority of applications are able to run completely unconfined. Trusted computing is a family of technologies that make it possible to create a verifiable, auditable, cryptographic log of exactly which software your system booted and exactly which software it then ran after booting. It makes it possible to ensure that your system cannot gain access to resources unless those resources are able to verify that your system hasn't been tampered with, which in a production environment is immensely powerful. But the complexity around it, the amount of work that has to be done to enable this sort of functionality is so far so incredibly site-specific, so user-specific, that its use has been fairly negligible. But moving on, because we're going to be talking about containers, I'm assuming that people here are enthusiastic about containers. You love containers. Good. People want containers for a variety of reasons. And one of those reasons is that containers are just easier to deploy. There's no more, well, I need to install these package versions, and ideally they need to be these specific package versions because we've been bitten in the past by things being broken in minor revisions, so we need to maintain our own mirror of various packages, and we also can't rely on third-party mirrors because those might go down. Containers avoid all of that because you just stuff everything you need into the container. There's the ease of development. I don't need to worry about validating my code against every version, every possible configuration, every version of everything, because, again, I can put the tested, verified environment inside the container, or I can indicate that the container is built on top of this base and then make use of it that way. So the mere fact that we are using containers allows us to think differently about security in a fundamental way. So when I'm talking about trustworthy containers, what I'm talking about is the idea that a container can be something that you can download, something you can verify, and something you can deploy, and you can trust the security properties of that container. You can have those be well defined. And this is particularly appealing in the sense that when we have multiple different components that we're deploying inside containers, we can define what the interfaces between those containers look like. We can restrict those. We can design those in a meaningful way. And this is, again, incredibly helpful, because up until now, when you're running a system with a lot of interconnected parts, a lot of the communication between those can happen in a bewildering number of ways. You've got applications that communicate with each other through IP, which is nice and straightforward. You've got applications that communicate with each other over local sockets. You've got applications that communicate with each other over FIFOs. You've got applications that communicate with each other through shared memory. You've got applications that communicate with each other by dropping files into a directory that another application then polls repeatedly. You've got all these ways for applications to interact with each other, and you don't know in advance exactly what those are. So when we're building a container, we can define the interfaces that we are expecting to be present. We build containers usually with the expectation that they'll communicate over IP, which is then a nice, straightforward boundary. It's something that we can control in a meaningful way. We know that if we install a container, it's not then suddenly going to start trying to communicate with other applications in some unexpected way, because it's not going to be able to. We're not sharing those resources. It just won't work. But also, containers let us treat different code differently. We've got a significant set of different kinds of constraints that we can put around containers. We can grant containers only the resources they need. We can grant containers only the capabilities that they need. When we do that, we can end up with containers running in a minimal environment where their ability to attack the rest of the system is, again, reduced. When you're trying to do this at a whole system level, it's much more complicated. You need to come up with a way of, well, when I start this application, it should be run with these privileges. And the application as shipped is probably not going to provide you with all that metadata, whereas there's much more of a tendency to encourage us to build containers which do only adopt the privileges that they require. And so a kind of outcome of this is that a lot of things that would normally be whole system level issues are not, well, the policy is embodied in the container or the container metadata, but the application of that is moved to the runtime rather than it being something where you need to attempt to apply policy to individual applications. So this is an example of this. How many of you have ever tried to deploy an application, an in-house application, on a system running SELinux? How many of you have enjoyed that? And this is not a complaint about SELinux per se. The functionality is vitally important, but it's very complicated, and that makes life more difficult. A typical SELinux flow involves you writing some software, and then you ship the software, and then a user tells you, well, I attempted to install this on RHEL, and it doesn't work, and I get a bunch of SELinux errors. And so you're reasonable people. You want to ensure that security is maintained. You don't want to just tell people to turn off SELinux because that would be a terrible thing. So you write some SELinux policy, and then you discover that that works on RHEL 7.2 but not 7.3, so then you write some more policy, and then you eventually get that working, and the user says, excellent, this all works perfectly now, thank you. And then you have to keep maintaining that policy in step with RHEL. But that's not too much overhead. And then you discover that people trying to run SELinux on SuSE have a completely different policy that doesn't work with your policy, and at that point, you add this to the top of your deployment documentation. So our ability to actually trust the software that we're handing to other people, or as admins, the ability to trust the software that we are being given is reduced, because in order to make this software work, we're having to compromise the security of the entire system. We're not even talking about a scenario in which this application is overly privileged. We're instead talking about an application that forces us to reduce the security of the entire system. Containers, this is much easier. You write your software. You put your software in a container, and then you ship the container. And then you don't get any complaints, because in this case, in the container world, the container runtime does the rest. And this is made much easier because, as I mentioned earlier, containers have much better defined semantics for communicating with other containers. By and large, they can't. So we don't need to worry about complicated policy. All we care about is writing an SELinux policy that says this container should not be able to touch the rest of the system, other than through well-defined mechanisms such as IP, or file systems that I have explicitly shared between multiple containers. And outside that, we can write a very simple policy that just says, no, you can't do that. But another thing that makes people very, and somewhat legitimately concerned about containers is the idea that containers have a number of bundled libraries. And like software itself, libraries are made of code. And in many cases, that code is C, and we're really bad at writing C. To be fair, C makes it very easy to be bad at writing C, but even taking that into account, the truth is that libraries often contain security vulnerabilities. And so people will quite legitimately ask, well, OK, you're downloading containers from multiple different third parties. How can we trust that this container does not have a vulnerable version of OpenSSL in it? And to be honest, static analysis of containers is a pretty good answer here. At this point, multiple vendors provide mechanisms for verifying whether your containers contain known security vulnerabilities. Quay now has Claire integrated into it, which will give you a nice list of all the known vulnerabilities in your software. Docker have similar functionality available in the Docker Hub, and then I believe that Black Duck also have something similar. Red Hat have something similar. So these are fairly straightforward mechanisms for you to look at, and then look at your containers and then say, OK, these containers need to be updated. I will update them, and then I will roll the updated containers out. That's pretty straightforward. That's not a disaster. You need to update more things than you did previously, but it's still pretty much an automatable process. And in some ways, this may actually be easier than the traditional solution of we update OpenSSL on every system. How many of you were bitten by the OpenSSL, I think it was 102G update, which was marked as a security update, but which also changed the ABI subtly, such that a small number of applications stopped working? Anyone here hit by that? Yeah, OK, a couple of people were hit by that. Not all OpenSSL use is equally critical. There are many applications that are using OpenSSL for things like its hashing implementations, or for RSA crypto, not for anything network-facing. And they're using it for local validation, local signature validation, local encryption. And in those cases, the fact that there's a vulnerability may not be, if the vulnerability is purely in its use in network-facing environments, that vulnerability is unimportant to that specific piece of code. But right now, you don't get to mix and match at the system level. Using containers, you can upgrade the containers that are network-facing as a priority. And then you can, at your leisure, verify whether the upgrade breaks any of the other containers, the containers that are using OpenSSL for much less security-critical purposes. We no longer have to have an all-or-nothing approach to security, which means, paradoxically, even though we have more copies of OpenSSL, we have much finer-grained control over what gets upgraded. We can build a reasonable idea of how much trust we can place in a container that has a vulnerable version of OpenSSL, whether that is still, in context, trustworthy. That way, we don't have to have scenarios where you can't apply a security-critical update until you've verified that 30 different pieces of mission-critical software running on the same systems are all OK with this upgrade. You can do each container one by one, and the moment you've verified that container, you can push out an updated version of that container. So in comparison to the status quo, containers have a lot of benefits. Not only do they allow us to have stronger imposition of security from the outside, we can also potentially end up with more aggressive updates of security-critical components. And even ignoring that, containers are, in many cases, better than the status quo of running multiple applications on the same system. Where right now, if someone compromises your web server, and if that's running on the same system as your database, it's much easier for them to compromise the database as well. Containerizing things means that there is a much stronger security boundary between your different components. Can we do more than this? One of the problems with security is that no security feature provides meaningful security if the layers below it are not themselves secure. Our ability to deploy trustworthy containers, containers that we can place trust in, is dependent upon the container runtime being secure. And the security of the container runtime is dependent upon the security of the operating system as a whole. Now, going back to what I was saying earlier, doing things in general-purpose operating systems is difficult. There are so many different ways that applications can communicate with each other. There are so many different ways a system can be configured. If you want to write a general-purpose security policy for a general-purpose operating system, you pretty much have to provide a very liberal policy to allow people to use that system in ways you have not considered, ways you were not thinking about when you designed it. If you don't have defined use cases, it's very difficult to build a completely secure platform, which means it's still difficult to place trust in the rest of your components. So even if we are talking about the security benefits of containers as a whole, it's very difficult to realize that additional security while doing so with a general-purpose operating system. So I have a somewhat heretical viewpoint here and say that maybe in a container world, we shouldn't be building general-purpose operating systems. We should instead be building operating systems that are custom designed to allow us to deploy containers in a more secure way, a more trustworthy way. And one aspect of this is that the operating system itself should not need to change. There should be no need to install applications in the operating system itself, because we're putting everything in containers. And in that environment, we don't need any writable file systems that can contain executables. We can have, instead, a cryptographically verified file system that backs our executables. If anybody tries to tamper with the system in any way, the cryptographic verification will fail, and the system will fail, and the attacker will not get anywhere. At best, they've got a denial of service. Google solved this problem with ChromeOS. They implemented something called dmverity, which is a layer that sits between the disk and the file system and has a set of chained hashes for each block on the block device. So if someone tries to tamper with the block device directly, the hashes no longer validate, and you get an I/O error when you attempt to read from disk. So there's no way for them to alter the state of the system. When I said trusted computing was difficult because there were so many different environments in which you needed custom configuration, where it was very difficult to build a meaningful policy around trusted computing without being an expert in the field, having an immutable operating system, again, solves this problem because you now have a strong idea of what the operating system state should look like during boot. You know what you expected the system to boot. You know what configuration you expected to have as it was booting. So these let us build an environment that is a trustworthy base, something that then gives us this environment in which we can then run containers and then trust that the containers will be adequately secured by the underlying operating system. And can we go further than that? So obviously, signed container images are vital here. People should not be deploying containers without a mechanism for verifying that the container images have not been tampered with. But signing is not magical. Signing says this container was at some point signed by someone I trust. A signature tells you whether someone trusted that container at the point in time where it was signed. A signature does not tell you whether a container is inherently trustworthy. So an example of this, if you have a container that you discover contains insecure software and you upgrade the software in that container, how many of you would roll your signing keys for the new container? Nobody. If someone's able to gain access to your control plane in any way, if someone's able to somehow cause your system to spin up an arbitrary container, what stops them from handing over the old insecure version of the container, which still has a valid signature? And the answer is nothing. And at that point, they're then able to potentially exploit that vulnerability and gain access to a system. Signing does not tell you whether something is fundamentally trustworthy. So we can extend the idea of trusted computing. In trusted computing, you have a small piece of hardware called the TPM, or Technical Protection, Trusted Platform Module. And the TPM contains a set of registers, and those registers contain the hashes of each component of the boot chain. The CPU verifies the first block of the firmware and puts that into the TPM. The firmware verifies the rest of the firmware. The firmware then hashes the bootloader hashes the kernel, and so on. So you get to an arbitrarily high level of the boot chain, and you know then what the system booted. There's no way that anybody should be able to construct a modified piece of software that will hash to the same value. So we can measure container images as well and push those into the TPM. And then we have a log not just of whether correctly signed images were booted. We have a cryptographically verifiable log of exactly which container images were booted on a system. And we can look at that log, and we can compare those hashes to the versions of containers. And even if someone does break into the system, even if they're able to break out of a container and obtain root on that system, they're not able to do anything to this log other than delete it. If they attempt to change the values in it, those values will no longer match the values stored in the TPM, and so you can detect that the log's been tampered with. So that gives you a completely verifiable audit trail. This allows you to say, this cluster only booted container images that I trust now. Not that it only booted container images that I trusted at some point in history. And we can go even further than that. The reality is that some containers are unequal to others. And that might be because they're running software that we trust less. Or it might be that they contain more sensitive data and we want them more strongly protected. Or it might be that most of our code is deployed in containers and doesn't have to face the public internet, but there's a small number of components that do need to face the public internet. And the question then is, well, are there additional security measures we can apply to these containers? And the answer is that yes, we can, in fact, isolate some containers more than we isolate others. And Intel developed a technology, a series of technologies that they describe as clear containers. And in a clear container deployment, a container is launched inside a lightweight virtual machine rather than inside a namespace-isolated container environment. That way, even if that container is compromised, you're no longer confined by the kernel only. You're confined by the hypervisor, by additional features in the CPU that make it more difficult for you to break out of that container. And you can deploy and manage these identically. From an admin perspective, the only difference between a clear container and a namespace container is, well, the VM-based solution takes slightly more resources, and also you can't bind sockets from the host into the guest. And in principle, there's actually nothing really stopping you from writing a VirtIO interface that allowed sockets to be passed through. But thankfully, I don't think anyone's doing, I really hope no one's doing that yet. But you get the security benefits that we would associate with full virtual machines, which is nice. So even in cases where we don't necessarily trust the contents of a container image as much as we might trust other containers, we can still bring the level of overall trust in the security of the solution up to a level that we're comfortable with by running it in this more isolated environment. If it does become compromised, there are, in fact, even forthcoming technologies that may allow us to automatically detect that a VM-based container has been compromised. So we can build secure container infrastructure. We can come up with things that allow us to build a more secure, a more trustworthy basis for our containers. And we can then build secure, trustworthy containers to run on top of that platform. And, sorry. This means that we can have a much higher degree of trust in the security of our deployments than we would have had with more traditional deployment scenarios. So with that, thank you all for paying attention. And I think we've got a few minutes for questions. Front there.
I understand you said... sorry, I'm coming.
Microphone.
I understand you said we can trust that the container does what it's supposed to do in a secure way. What about securing the access to the container?
So securing access to the container in the sense of the network access?
Well, let's say if I have a container that accesses the database, what if the access to that container is compromised and affects the database?
Right. So right now, we don't have particularly strong mechanisms in the general sense to have a level of fine-grained control that was allow you to tell the difference between a container that is, under normal circumstances, authorized to access a service and a container that can still access that service if it's compromised. As I said, there's some stuff that we're working on that will allow us to detect that in some of the VM-based containers. In the more general case, if you're willing to accept some degree of performance overhead, it is conceivably possible that we could gain some of the same benefits in a namespace-based environment. But I don't think we have a good general solution for that yet. Something back there?
Two questions. The first one is, what's the difference between running a VM with an app with, say, just enough OS versus running a container inside a VM, which was the last scenario you talked about? And the second one is there ways to restrict which container, can container of this type talk to another container of this type, but only on certain ports, only with certain protocols, being able to restrict how they talk to each other, because in a multi-layered application, you might want to have that.
Right. So to your first, the idea between just running a VM with a minimal operating system and a single application in it, they're basically identical. The question is really more about your tooling. If you're using a container-based environment in general, then using VM-based containers means you don't need to add any additional tooling to that. If you're right now primarily VM-based, if you have no interest in having a heterogeneous mixture of VM-based containers and namespace-based containers, then there's no particular advantage to using the containerized version of it. But if you're in an environment where you are using a lot of namespace-based containers and you have if you would occasionally benefit from having a VM-based container there, then the fact that you don't, it's just, so Rocket implements this, you just pass a different flag to Rocket, and everything else looks identical to how you would bring up the containers in a normal case. As to your second question about more sort of fine-grained control of which containers can talk to which other containers, I'm not really much of a networking person, so I don't genuinely know what the state of the art is in this respect. But certainly, you can set up firewalling rules that would allow you to limit what access any specific container has to other containers and to the rest of the world. So it's certainly technically feasible. It would surprise me if nobody has done work in this field, but it's just not one that I have paid a great deal of attention to.